All right, so we can begin. Today, what we want to cover is friction cone, right? So it appears to be a small topic. You could theoretically think we can cover it in like 5-10 minutes, but there is quite a bit to it, especially in terms of just like representation, how various other aspects of its of how we can use it, linearization. I think it would be not only sufficient for the lecture, it might even kind of go a little bit outside of the allotted time. So I'll try to make sure we kind of make it fit into what we have in terms of this lecture. All right. So let's begin. And this is, I think, our first time discussing friction in this, at least dry friction, in this class, unless I'm mistaken. So let's begin by just quickly reminding ourselves what friction is, right? So dry friction, as opposed to, for example, viscous friction, which you think of as just the force that dissipates energy, right? Dry friction is an effect, is a physical effect, okay? It appears to us like a force that prevents sliding of rigid bodies, right? So here, I understand that those type of minor details don't usually register really well, and they appear to be a little bit away from the practice. But I think it is important to keep in mind. Dry friction is a physical effect, right? It's not a mathematical, how should I put it, mathematical quirk or just natural consequences of some axioms that we like to use, etc. It's a physical effect that we are trying to describe, okay? So in a sense, a lot of what we think and say about it is closely tied to how the actual physical effect works in reality, okay? And this, whenever something like this happens, it can lead to a lot of strangeness in mathematics, because as opposed to math, which is always very beautiful, comes out of axioms and preserves a lot of symmetries, etc., physical effects are not always, especially depending on what kind of approximation you use, etc., not always lending themselves well for this type of structure. Okay, so it's important to keep in mind it's a physical effect first and foremost, and it appears like a force, right? It's also important to keep in mind that force itself is a mathematical abstraction, right? The idea of a force, at least in mechanics, when you're talking about classical mechanics, is a mathematical abstraction. We could discuss how real forces are in terms of, let's say, theoretical physics, when we talk about like gravity, electromagnetism, etc. But in mechanics, in classical mechanics, forces usually are quite clearly a mathematical abstraction, because what we usually think of as a force is two rigid bodies touching themselves, like having a actual physical contact, right? And you think that there is a vector of force, like some sort of direction and magnitude, which acts on both bodies in opposite directions, right? Equal magnitude, Newton's law. Okay, so we think of like two rigid bodies acting on each other like this. In some cases, it's like wind or water producing force, drag, etc. Right? Sometimes it is directly gravity. But this is a particular example that is quite typical, especially for us in contact-aware control. Reaction forces are like that, right? Two rigid bodies acting on each other. Problem is, of course, that there is no such force in fundamental physics. What you have in fundamental physics is various electromagnetic forces, which would prevent, for example, molecules from moving around in a crystallic structure, or molecules of metal to move around. So on a larger scale, you can discuss it as elasticity of a material. Depending on the material, it can be elastic force, can be something else, not necessarily elastic force, right? So we have we have a lot of underlying structure that actually makes those two rigid bodies produce those forces. And all of this we can abstract away in classical mechanics. We don't like to think about it, okay? Like we don't want to think about how on a tiniest scale the floor is being deformed by our foot, and that deformation leads to some sort of a tension in the floor structure. Maybe like an entire beam somewhere kind of goes up and down a little bit, and all of this produces this net reaction force, right? We don't want to think about it. We want to just say action equals to reaction. Okay, we have some sort of dynamic scenario. We can compute the reaction forces. All of this is fine usually. All of this is fine. We don't necessarily have to think about those things, right? Computations, as you know about classical mechanics, computations can be done without considering those smallest scales, right? Of, not necessarily even smallest, even small scales are not necessarily needed to be considered, okay, when you talk about forces. With friction, though, you have to run the same logic one more time, okay? So while you can get away saying, okay, we don't have to consider those deformations, etc., when you think about reaction forces, and there are reasons why. The reasons are that reaction force as a approximation acts quite as well as would, like finite element model would act or something like this, right? So you can say using reaction force as a model is fine. You have to run the same logic one more time when you talk about friction, because it is a different force. You cannot just extrapolate your intuition from one type of physical interaction to another. You have to justify it one more time. Okay, so this is what I want you to keep in mind, that we have to somehow one more time consider our assumptions about the force. Keep in mind that the idea of a force itself is just the abstraction that we use in classical mechanics. It is not a fundamental force in the same way as gravity is, for example. All right. Typically, dry friction is modeled as a constraint. Okay, as a constraint. What do we mean? Oh, remember when we set a foot on the ground, we assume the foot is not going to move down, the foot is not going to move sideways. So it is a constraint. We say the position is equal to its current position. It's not going to move. Constraint, okay? And there is additionally a condition of changing static contact to sliding, okay? There is, of course, a separate condition on breaking the contact at all, or, like moving the foot up. There should be a condition on that too. That is a separate thing. We will discuss it next lecture. But there has to be a condition of changing the contact from static to sliding, okay? Because as you can imagine, friction force is not a glue. It's not going to prevent us from sliding. I mean, sliding occurs as a physical phenomenon. Two rigid bodies can slide one against another, right? I'm doing it right now. You can see one of my hands slides against another. So sliding occurs, and we have to have a model for that. And we cannot just have a constraint, like a rigid constraint, as a model for dry friction, because without a condition of how it can be broken. Otherwise, our model just doesn't correspond to reality very well. Okay, so there are a number of friction models, and you won't be surprised, hopefully, that there are a number of friction models. And they often differ in describing how the force behaves before and after the sliding occurs. Yeah, and on the condition of when sliding can occur. Okay. So a typical model is Coulomb friction. Right? This one is basically saying that tangential component, so what we call friction force, is maximum value of it is proportional to the normal component. So, and once the sliding occurs, this like inequality becomes equality, right? There are other models such as stiction, where you have two different coefficients for dynamic friction, so sliding and static friction. Stiction it describes well the situation where you try to move your cupboard and it kind of doesn't want to move and then it jerks, right? This kind of situation. There are other models of friction, quite a few of them. Right, but one of the most popular models in robotics is the model Coulomb friction with a friction cone. Okay, so this model requires the friction force to stay inside a cone. Okay, that's what we are going to discuss today. Okay, let's see. First, we start with a two-dimensional example. So, in two-dimensional case, derived friction can be described simply as this inequality, where you have absolute value of the friction force is less than or equal to normal reaction force times a friction coefficient. Okay. And since it is absolute value, like all of those are scalars, since it is absolute value, we could replace it with two inequalities. Absolute value for a scalar can always be replaced with two inequalities. And the way we could do it, let me see if I can write it. So f tau, I would write it as ft would be less than or equal to mu fm, right? That is the case when f tau is positive. This the situation is completely well described by that equation. And then minus f tau less than or equal to mu times fm, but with a minus sign. Okay. What is this description? Well, if we invert the sign, if we multiply it by -1, what we have is f tau is bigger than mu times fn, right? That's correct? Let me, no, I think I made a mistake. There's one mistake, yeah. Let me correct it. Yeah, this was a mistake. Okay. So if we invert the sign, what we say is f tau would have to be bigger than minus fn, right? So you minus f tau, yeah, I think that is a good, maybe better way to say it. So minus f tau is still less than mu times fn. That is, if f tau is negative, we can invert the sign, and the inverse, and it would still have to abide the original constraint, right? It should still be less than mu fn. In this case, fn is always positive, right? Fn is always positive. We can just assume that is by convention. We say that fn is positive. We don't have to do it like this, but it makes sense for simplicity because you have normal reaction force has to be pushing off the ground. Okay, so let me just draw it so you would understand what I mean. Okay, let's say this is a surface. Okay, a normal reaction force has to be like this. Okay, normal reaction force absolutely cannot be like this, right? So it has to push off the ground. The ground cannot pull on the body, right? So the normal reaction force always comes facing away from the ground. Okay, and why, for example, I don't draw it, let's say, like this? It sounds like it is possible to. Well, the problem here is that it is like this blue arrow would be a combination of two forces: normal reaction force like this, and separately a friction force like this. Okay. So that's a problem. That's a problem. We shouldn't. We shouldn't. Yeah. apologies. Zoom is very difficult to work with nowadays. The annotation system, they broke it for some reason. So this blue line sounds nice, but it is actually just a combination of two different forces: friction force and normal reaction force. So we're talking about normal reaction force right now. It is always one direction, normal to the ground. It's not like a family of directions. It's just one direction, one line. Okay, and it can be positive or negative, right, along this line. And by convention, we always say that the direction in which the correct direction is positive direction. Okay, so the direction away from the ground is positive direction. Just a convention. We don't have to do it this way. It would just simplify our thinking. Okay, so that is the idea. So that's why I have this last equation here, right? And if this last equation holds, that means that the right-hand side is always positive in both of those. That means that here we're saying that it's a positive number, always either like a positive number, but less than FM, or a negative number, which can be anything. And here we say it is either a positive number, that can be anything, or a negative number, but it has by absolute value to be less than Fn. So that's how those two together form this equivalence of the system. Okay. Geometrically, this friction cone is a two-dimensional cone. It looks like this. Looks like this. So it's basically two lines, and admissible directions lie all within those two lines. Let's see if I can draw it. So the admissible directions are all one second, I will just try to see if I can draw it. Yeah, all here. This is all admissible directions. Okay. Oh, that's it. That's two-dimensional friction cone. Quite simple, and I think equation 1 is familiar to you from, let's say, high school physics. Okay. At least should be. Equation 1 would probably be something that you recognize as Coulomb friction model. Now, two-dimensional case is very simple, but we usually would have to do with three-dimensional cases. In 3 dimensions, friction force, so we would call it F tau, friction force, together with normal reaction force, okay, form contact reaction force. Okay, so friction force together with normal reaction force forms a contact reaction force. So contact reaction is equal to normal plus friction. And it is not surprising because friction force is a tangential direction, okay? Normal reaction is a normal direction. Together, they form R3, okay? So normal direction by definition is orthogonal to tangential direction. Tangential direction has 2 dimensions, right? Like, let's say X and Y. And normal direction gives you Z. So together they form R3. So any vector in R3 is a direct sum of those vectors in normal direction, tangential direction. So not surprising that any force can be decomposed in those two components. Now we can choose to represent a reaction force in some nice basis B. Okay. And we can form this basis by, for example, concatenating normal direction N and 2 tangent directions T1, T2. So let me draw it for you. And 1 second, I will just quickly create some space. Okay. Now I can draw it. So normal direction, I will show it as a red line. Tangential directions, I would show it as 2 green lines. Okay. So you can imagine you have this green plane, that is where friction force lies. It is tangent to the contact point. And then you have this red direction that is normal to the contact point. Okay, that's where normal reaction force lies. If we concatenate them, we get B, matrix B. So the basis B. Here it is. Basis B. The same basis here. And in this basis, coordinates of the forces are Fn. So the scalar that represents the value of normal reaction force, F tau 1 and F tau 2, those two scalars, their square root of the squares, sum of the squares, right? Tau 1 squared plus tau 2 squared square root. That would be magnitude of the friction force. Okay, so they represent together coordinates on this green plane. They represent both the friction force itself. But so let's say here's the friction force. Coordinates of this friction force would be tau 1 and tau 2. Okay, so you can say they represent direction and magnitude of the friction force. Okay. If this sounds esoteric, just spend a little bit of time thinking about this, what I wrote here. What I'm trying to say is FR, F reaction force, is equal to normal direction times magnitude of the normal reaction force. To T1 times F tau 1 plus T2 times F tau 2. Those are coordinates of friction force times the directions of the friction force. So coordinates on the tangential plane should be clear enough from just geometric perspective. All right, so if we have this, let me use the arrow. If we have this normal reaction force, then total force we could imagine would be something like this, right? I can say this. How it is. Okay. Now this blue arrow will be total reaction force. Okay. Okay. The takeaway from this slide is just that we could represent total reaction force in a basis formed by n T1, T2, and the coordinates would be very meaningful. It would be Fn, F tau 1, F tau 2, nice coordinates that have some kind of meaning. Okay. Okay, all right. Now we can write a friction cone constraint in the following way. What is this? Well, we can say F tau 1 squared plus F tau 2 squared, square root of those two, should be less than or equal to Fm times mu. So you can see this is like a scalar or coordinate representation. What I'm trying to say here is that we could just find, if we know coordinates of each of those forces, we can just write it in this very simple manner. You know, the left-hand side is just a definition of what it means to be like a norm of a vector, right? The left-hand side, the right-hand side is just a mu times Fn, right? The magnitude, all is very clear. The fact that there's a cone should also be clear. It's more or less a definition of a cone, like norm of a vector less than or equal to this. So how should let me, I guess, to avoid mystification, let me just write it like this. This equivalent to saying, okay, Tx less than or equal to m transpose x, right? So, and this is a second order cone equation, right? But equation 4, you can recognize it as a cone in its own right. If you understand F tau 1, F tau 2, Fn as coordinates in R3, this would describe a cone, and you can quite easily prove that it is one, right? But also, you can easily rewrite it in this way that I wrote above, and that is the definition of a second order cone. So, okay, all right. So we can call it element-wide description. It's very nice, and some people use it. So you would see this in the robotics literature. This is being used quite often because it's very simple. That's what people like about it. The problem is, of course, that somehow in this definition there is an embedded B matrix, this transformation matrix. It is not explicit; it is implicit. It is somewhere inside. And we have to remember that it exists. So easy enough to forget about it, and it can cause problems. Okay. So this is a simple definition of friction cone. Now we can write the same constraint, exact same thing, like this. And remember, this is what I wrote previously on top of the slide. Let's look at it carefully now. What is this? Well, remember we said, and let me, I guess, go back 2 slides. We said that Fr is equal to n times Fn, T1 times F tau 1 plus T2 times F tau 2. This part, F tau 1 times T1 plus F tau 2 times T2, that is a friction force component. So if we multiply this by this, we get friction force F tau. Okay? The norm of F tau has to be less than the norm of Fn, right? So less than this component, Fn times n. Okay. And since all of those vectors they're normalized, we assume that B is orthonormal basis. Okay, so n, Tn, T1, T2 are all normalized unit vectors, right? We could interchangeably consider norm of F tau and norm of F tau 1, F tau 2. Okay, those norms will be equal to each other. Norm of Fn will be equal to norm of Fn scalar. Okay, so this and this, their norms would be exactly the same. So their norms would be the same. Their norms would be the same. Okay. So we have options here, and if you want to compute the norm of this pair, what we can do is we can multiply this vector by this part of the basis, okay? And what we will get is F2, F tau 1, F tau 2. Remember, this is orthonormal basis. So since it is orthonormal basis, we can say that, let me write it here, that the coordinates, I will just write it as coordinates are equal to B transposed F R, okay? So this Fr, we can multiply it by B transpose, or you could say we multiply both sides by B transpose. It is possible since B transpose is full rank. B transpose cancels here until is left here. So that's how we get coordinates Fn, F tau, F tau 1, F tau 2. But if in particular what we want is just F tau 1, F tau 2, we can use like some sort of selection matrix, etc., which would at the end analysis equal to multiplying both sides by T1, T2 matrix, right? Transposed, of course. Just, you know, if you want to see it, do it, you would see that T1, T2 multiplying by itself would produce identity matrix. This n, both of them cancel to 0, etc. So just do it, see how it works. Okay. Right. So this is what we do here, and we get here basically this F tau. Okay. Here, what we have on the right-hand side is normal reaction force. That is Fr times N transposed. That gives us normal reaction force. This is the same. So this is the same as here. Just instead of coordinates, we got the recipe of how to get those coordinates, right? Okay, that's a recipe of how to get them. Okay, all right. Now we can call it a vector description. So the advantage of this description as opposed to this description is it uses a single variable. So notice the variables in this description are fr. We don't have f tau 1, f tau 2, fn, which you have to understand what they mean and so on and so forth. Here, there is a vector in R3. There is no hidden basis in which those components are expressed. It is quite explicit here. So we can, without any additional work, use it right away. Right? We don't have to ask ourselves, but what did the programmer understand by the basis in this particular case if we write code? No, it's, here is a basis, quite explicitly. And here is the vector. It can be anything in R3. And it takes form of second order constraint. So for your solver, this is directly in the correct form. Okay. Now, there is one thing that you have to take into account. T1 and T2 would usually not be given to you. Like the problem would not contain them, right? Well, N can be naturally recovered from the surface. Like you have a surface in some kind of representation. For example, you can know that the surface is vertical, horizontal, and then N is vertical. Or you can get some kind of point cloud description, which would naturally produce you normals. Those are typical situations. You would have normals. T1 and T2 you would usually not have, because they're arbitrary. Like you have a normal, you can put them like this, like this, like this. So basically, you can imagine like these two fingers are normals, and thumb is tangential vectors T1, T2. N is a normal. I can rotate, nothing changes, right? The basis T1, T2 can be rotated without any physical change. So that's why T1 and T2 would not usually be given, because they don't have separate physical meaning from each other. They only mean something as a plane. Coordinates on the plane are arbitrary, up to rotation, okay? So you cannot expect to have them, is a problem. Okay, so one can easily find them as, for example, left null space of normal vector, okay? So that would be this matrix T is equal to T1, T2 is equal to left null space of N. Left null space of N is equal to null space of N transposed, right? So that's one way to do it. And then your equation 5 becomes equation 6, where you have T times FR less than equal to mu N transposed FR, okay? So if this is something you're happy with, you can do equation 6. Remember though that this operation null space is SVD decomposition. So you pay for this by performing SVD decomposition, which is not something you want to do at high frequencies because it is expensive. Okay, let's move on. Let's see another description. So there will be quite a few representations today, so we have to be comfortable with that. Now, another way to do it is by considering projections. So I can say here's a projector of FR, so the projector onto tangent space. So P tau projector on the tangent space. So this P tau projects FR onto the tangent space, so it flattens it onto the tangential plane. This projector Pn projects Fr onto the normal direction, so it kind of states, puts it onto the normal plane. And they are orthogonal projectors, so they have properties of orthogonal projectors. They don't shift anything that is already in the correct subspace, and so on and so forth. All right, how do we get p tau? Well, it is like this, right? I minus n transposed. How did I get this formula? Did I look it up in the scientific literature? You don't have to. It's actually quite obvious. There are two obvious ways to how to read this formula 8. First, you can read it as, let me just walk you through it. I think we already had this exercise previously on different course, but let me just walk you through it twice in different ways, okay? One way to read this formula. You see this n transposed, okay? Transposed for orthonormal basis is the same as inverse, okay? Or pseudo-inverse. They're all the same. Right? Same as pseudo-inverse, not as inverse. Sorry. So this n transposed is in the second position. This tells you that n transpose is a projector onto the column space, right? If the transpose was in the first position, it would be a projector onto the row space. You can memorize it, or you can just quickly think of how it could be derived, right? How it could be derived. So again, if you worry about what it is, like column space or row space, you can think like, okay, this n, this last part, would get whatever you give it as an input and push it into the column space of n, right? So this whole operator has to take input and put it into the column space. It cannot help but do anything. It cannot do anything else. It pushes stuff into the column space. So it has to be a column space projector. That's like a way to memorize that transpose at the end would be a column space projector. Okay. Same with the row space, but I would just avoid spending more time on this. All right, so this is a column space projector. This is I minus column space projector. So basically, when you say I minus a projector onto the subspace, what you get is the orthogonal complement of this projector. Column space orthogonal complement is the left null space. So overall, this is left null space. So that's how you can construct it. That's how you can memorize it. Clearly, it is a left null projector. And what is the left null of normal space? Tangent space, right? So this is a projector on the tangent space. That is one way to do it. There is another way, and it is equivalently profitable. So please pay attention to the second explanation as well. It is good. It's good. So let's just consider what happens when you multiply FR by this vector here by Fn. What we get is basically what we also call a projection. What we get is a coordinate of Fr on the axis n. Okay, so basically you can say if you want to represent Fr in terms of orthonormal basis, and one of the axes is n, would be a coordinate along this n axis. Okay, good. That's what happens when you multiply it by Fn transpose. Then you multiply it by n. What happens now is that you take this coordinate, multiply it by n, you get vector now in R3 that is aligned with this n axis, so in normal direction, okay? And its length is exactly equivalent to the length of Fr projected onto this axis, okay, right? So basically, this is like a normal component of your Fr vector. And then you say, okay, good, we have this normal component. Let's subtract it from Fr. Fr times I is Fr. So we subtract from it its normal component. what is left? Well, what is left is clearly tangential component because we subtracted normal component. We subtracted the projection onto n axis. So that's how you can again see that this guy is a projector onto the horizontal, like tangential space. Okay, by the same logic, this is clearly a projector onto the normal space. So just like that, just like that. All right, all right. And you can see that they are orthogonal complements of each other. So that's how you can get this, right? It will work just as well. Here is the advantage is that both vectors here inside are three-dimensional. If this is important somehow for you, here you go. Now, the problem is, of course, we don't want to compute so many entities. Especially we don't want to compute here this norm, because ultimately we don't have to. Like, we can get away with computing the dot product there. So what we can do is, for example, we can combine this with the previous slide to get this description downstairs. What is the description? Well, p tau here is being preserved. But now the right-hand side is directly from the previous slide. Direct from the previous slide, just a dot product. Notice here we don't have SVD and we only have one norm. So in fact, this is maybe the most economical description that we have. Also, here it wouldn't matter much, but you could compute this, open the brackets, and compute it like f times, n as a dot product. So it would be 3 multiplications, 2 additions. Then you can compute multiplication by n. That would be 3 multiplications. And then you compute this minus, that would be 3 subtractions. So not a lot of operations. So instead of, for example, opening this bracket, doing computations inside the brackets, which would be only this minus sign would be 9 for the like basic operations, right? So this would be how many? I believe 9 multiplications. This would be, I think that would be maybe quite a few. Like there's 9 components to be computed, and I think each of them will be computed with, unless I'm mistaken, with 1 multiplication. So there will be 9 multiplications. Here's 9 subtractions. So already much more operations. So if you want to cheapen your computations, like expression 10 looks nice, especially if you do it right. If you order your operations in an optimal way. Why is it important? Well, because it is online computations. Those computations would have to come online. A lot of the control has to be done online. And this is one of those. So that's why it is important. Okay. Now, all of this, like, let's just review. This, and this, same stuff, but in different ways. It is always describing friction cone. Friction cone, remember, is this kind of entity, right? This kind of entity is, to work with it, you have to use what we call SOCP. If you want to use it in optimization, second order cone programming is expensive. And friction, as I said, is a physical effect. That means our model that has like coefficient of friction, etc., isn't necessarily accurate, right? For example, it is possible that friction coefficient is directional. Like it would be one direction, it would be one friction coefficient, another direction is a different friction coefficient. In fact, we have to be conservative in order to make sure that we don't violate the cone, because we cannot rely on friction being uniform. So often enough, it makes sense to, let's say, instead of this friction cone, kind of assume that we have maybe a small one inside. Right? So we're already kind of tempted to be conservative with how we estimate friction. And then it becomes a big question, why do we need to keep this very nice pristine geometry at the expense of solving SOCPs when we can linearize, replace this nice geometry with, let's say, something like a square, for example. I apologize for making not a very nice square. I blame Zoom as usual. This is its latest update. Right? Something like this. Right? We can just replace cone with a square, and we say, okay, good enough description of a cone. And if this is good enough for us, then we can save SOCP programming and instead do linear or quadratic programming, right? Why not? If this is good enough, it would work, and we would have this simplified geometry computations. Okay, let's see what we can do with it. Okay. So what we want is to replace second order cone with a polytope. Right? So with a polytope. So a figure with faces. It is linear faces, no curvature, just linear faces. Faces, vertices, etc. So this allows us to go from SOCP to QP, but at the cost of being either under approximation or over approximation. So let's understand those first. But let's first see just how it looks. So this is a polytope that approximates a cone. Notice it has faces. Like here's a face, here's another face, face. It has faces. The tip of the cone is still there, right? Here I represent with those red lines normal directions to each face. So each face has its own normal direction, which would be useful when we construct the cone. All right, so this is how the cones look. And notice the more faces we have, the closer it will be to original cone. The geometry become more and more smooth. Okay, the angles will become closer to, how should I put it? They'll be less obvious, less sharp. Okay, they'll become bigger. Yeah, they'll become bigger. If we have fewer faces, they will be sharper, the angles here, and the cone will be more different from the approximation will be more different from the original cone. But more faces means more complexity. And we have to wonder if we need more faces. Like we can, just the question, do we need to? Okay. Now, when approximating friction cone, we want to retain some of the properties of the geometry, right? But we have to choose which ones we retain. So let's just consider two possibilities. Under approximation, or which is the same, inner approximation, implies that the approximate cone, CA, okay, approximate cone, lies inside the original cone. Okay. So any point that is in the approximate cone would also be in the original cone, but not vice versa. So there will be points inside the original cone, such as Y, which is like, say, inside the original, which would not be inside the approximate cone, right? So inner approximation. Just to give a very crude example, so original cone, right? Okay, original cone. And let me change color. Under approximation looks like this. Right? So the cone lies inside. Except we don't like this kind of like sloppiness. We want it to be as close to the original cone as possible. So we make sure that it touches the boundaries at least. Okay. So this is the under approximation. Now over approximation is or out approximation. Okay. It is when the original cone lies inside the approximated cone. Okay. So meaning that any point in the original cone is also inside the approximated cone, but there are points in the approximated cone which are not part of the original. Okay. That on the same picture that I drew can look, for example, something like this. Let me see. Yeah, something like this. Okay. So this would be over approximation. Okay. So the red one is over approximation, the brown one is under approximation. Why would we ever want over approximation? If we want to guarantee violation, if we want to guarantee that we start slipping, let's say we want to guarantee that we go beyond friction cone and we start sliding, that is when we want over approximation. If we want to guarantee stability, so we don't start slipping, we want under approximation. Different tasks. It's not the same task would never require you choice between them. It's always different tasks. Okay. And we assume that the approximation is tight, so we don't just do random stuff, right? We assume some sort of tightness in the approximation. We don't just make them huge or tiny, right? The tightness of approximation depends on the number of faces, but given the number of faces, we want to be as tight as possible. If we think that our mu is too generous or too small, we can work with it directly, but that has nothing to do with linear approximation. That is more of a question of modeling the original friction. Okay. All right. Let's look at it. Okay, here's just the illustration, better illustration of what I was drawing. This is the original cone, over approximation, under approximation. Tangential direction, what I call T1, T2. T1, T2. Normal direction here. Okay. Now, how do we do it? Well, let's consider one way, and that is by using H representation. H representation is a half space representation. You probably remember it. Basically, we represent a polytope as a collection of linear inequalities. Each inequality represents a face of a polytope in the simplest case, right? It represents the face of a polytope. So here is the original set, right? That is a conic set. Here is the H polytope set. Let us quickly remember how to read this. All X such that this SOCP constraint holds are inside the cone. Okay. Here how we read it. All X such that A times X less than or equal to B. That is H polytope. Okay. So set notation. Okay. And you can see that the difference between the two is that first has SOCP constraint, second has a linear inequality constraint. SOC, linear inequality. Okay. Now, there are many ways to generate A matrix and B vector in H representation, right? Like vertex enumeration would be obvious choice. Right? But vertex enumeration can be costly, and we are not going to do it here. We're going to, and it also requires a polytope to be closed. We're not going to do it here. Okay. So first of all, assuming that normal reaction force can be anything positive, right? It can be as big as we want, it just cannot be negative, right? Then if this is so, then all faces of the friction polytope pass through the origin, okay? So origin lies on each face of the polytope. Extremely important detail. Why? Well, let's think about it. So each face that basically lies on the boundary of a half space, and the half space is represented this way, right? Those are half spaces, like AX less than B. Each line in each row in this equation is like this: A sub I dot product with X less than B sub I. Okay. So those are half spaces, but the boundary is when AX is equal to B. Okay, AX is equal to B. Here I have a typo. Let me correct it. Let me correct it. One thing. Here, like this. Like this. Okay. So the plane on which the half space lies is represented by equality. Okay. So inequality represents the half space. So half of the Rn, right? The equality represents the boundary of this half space. So those boundaries are represented as A sub I transpose X equal to B sub I. Okay. But since X equal to 0, since this guy lies on each of those faces, we can substitute it here, and the equality should still hold. But A times 0 is 0. So that means that B sub I is 0. That means that B is 0. So this vector is 0. Very interesting, right? We found that we don't need to find A and B, we only need to find A. Nice. Okay. Do you have questions about this? If you have, go ahead and ask. Okay. So now the key requirement for us is to do as little computation as possible. Okay. So there are hundreds of ways to do it easily with more computations, but we want to avoid more computations because we have to construct it online, right? So one way of doing it is by starting with generating points V sub I on level set of a cone. So let me remind you what I'm talking about. Here's a cone. Okay. What I want to do is draw a number of points on its level set. So level set is when the right-hand side in the second order cone equation is equal to a constant, right? Like we get some equally spaced points on the level set, and we call them V sub I, right? What does it mean for them to be on the level set? Mathematically, it means that N transpose V sub I is equal to N transpose V sub J for any points of this set, right? Of this level set, right? So in the normal direction, they are equally distant from the origin in the normal direction, okay? Not in the Euclidean sense, in the sense of projection onto the norm. Okay. We can describe a plane that passes through the tip, right? The tip here, and any 2 points here. And how would it look, this plane? Let me use a different color. Oh, quite obviously it would look, let me use something brighter. So quite obviously it looks like this, right? This intersection of the plane with the cone, that is what I draw here. Okay, we can describe this plane by its normal vector. Its normal vector m sub I. And how do we find this m sub I? Well, we know 2 vectors on this plane. The vector from 0 to vi and from 0 to vi plus 1. How do you find the normal to the plane? Cross product of those 2 vectors would give us a third, which is normal to them. And since it is normal to 2 vectors on the 2D plane in 3D space, it will be normal to all of the other vectors on this plane. So it will be normal to the plane. So we just get a cross product. That's it. If this explanation was too fast, again, I recommend you go through it by yourself. You'll just remember basic stuff from vector algebra is useful and nice, right? But 2 vectors on a plane, cross product gives you the normal to the plane. Okay. All right. Now we have mi, which is a normal to our plane. So it would be on this picture, something like this, right? Like a normal to this plane. Okay. So this normals m sub I, approaches we have again type of m sub i's are actually equivalent to a sub i's up to a sign. So they don't necessarily have the correct sign. They have to point away from the normal direction. They have to point away. But the cross product doesn't guarantee you that. Okay. So to make sure that they are pointing out, we can do a trick. And this trick, I'm not sure if it's optimal. I think there might be a better trick. So if any of you want to come up with a better trick, like less computations, please tell me, submit it or whatever. That I would definitely great. Okay. Up to you, if you want to exercise your geometry, right? So the way it is done here is like this. We have our original vector. What we do is then we take the sum of those 2 vectors. We can divide by 2, but it won't change anything in the computation, so that's why I don't divide by 2. The sum would be like basically a point. If divided by 2, it would be a point between them, right? Okay. And then what we do is, I guess we could have just taken the vi with vi sub 1 plus 1, I'm not sure. Then we multiply it by p, which did I explain anywhere what p is? P should be a projector onto the horizontal, so onto the normal direction, right? Multiply by p, projector onto the normal direction, and then we multiply by m, so by itself. What does it do? What does it do? Essentially, the way you can think about it is like this. I don't know if I need to explain it, because I think this trick is kind of clumsy. I'm not sure if this is worth your time, but let me explain it anyway. I will just try to be quick. So you have, let's say, this point between vi and vi plus 1, all right? Okay, so you know for sure, and let's say you have now this m sub I pointing this way. Or it can point this way potentially, right? The direction itself, so the direction as a line is given. It's not going to change. Only the sign can change. So you don't know which way it points. But what you can clearly see is that it should be have positive dot product with v sub I. That is for sure true. But except both of them can have vertical direction and the normal direction, which we don't care about. We talking about this like in the tangential plane. So what I do is I projected first both of them into the normal in the tangential plane, like this, right? Both of them are projected on the tangential plane. And then I say, okay, let's find the product. If the product of those dot product, if the dot product of those two projections is positive, then the sign is correct. If it is negative, we multiply, I would take the sign, multiply mi by the sign, and we correct the sign this way. It just happens that when you project both vectors, you have two projectors, and in the dot product, those orthogonal projectors are equivalent to one projector. That's why we only have one P here and not like two of them. Right. This is awkward. I'm not sure if I like this method. I'm just proposing it as one. I'm not sure if I have seen more elegant ways to do it, but I suspect there should be more elegant ways. Yeah. Anyway, is a sign question. Those should be solvable easily. If you want to solve it, propose. Okay. So this is how we can. That's how we can, for example, do H representation. All right. Sometimes what we can do is we can want to add the limits on maximum minimum normal reaction force. So for example, we don't want normal reaction force to be like too low, being afraid that the contact will break. And we don't want it to be too high because we think it is unrealistic. So we can set a minimum and maximum of normal reaction forces this way. This would effectively cap the friction cone. Okay, so this would appear as a cap on a friction cone. Okay. Now, what we can also do is we can do a vertex representation of a friction cone. Vertex representation of friction cone. That is alternative to H representation. And here, what we do is we generate a friction cone as a combination of vertices, V1, V2, V3, etc. How is it done? By the way, including the origin. This time it includes the origin. No, it's not just vertices on the level set. It includes the origin. Well, in the set notation, it means all x such that x is equal to linear combination of the vertices, where the coefficients of the linear combination sum to 1, and they're between 0 and 1. Okay, this is called convex combination, and you have already seen it. Okay, so this is the way to do it as a V representation. Now, let's be more specific. What is the difference between those two? Well, H representation is basically linear inequalities. So it's simplest one to evaluate. V representation is equivalent to solving optimization problem, much harder to evaluate. V representation naturally includes upper limits on normal reaction force, because you choose V1, V2, V3, etc. They can represent upper limit. Right? It depends on the height of those vertices. Yeah. And the representation skips construction of half-space normals. Right? So the previous slide, remember when we were thinking about sign, all of this we can skip with the representation. We don't have to do it. That is a great advantage. And a lot of people in the papers that I have read recently use specifically this representation. So the representation is more popular in practical work. My impression, at least. Okay. So we don't have a lot of time, so I'm going a little bit faster, but let's see if we manage to get through it. So one thing that we may want to do is to lift this cap on the maximum normal reaction force, because it's kind of silly. Like, if we don't want it, why do we have to have it? And the way we do it is by simply excluding this constraint, right? So we leave it as alpha sub I bigger than 0, and that's it. We don't ask it to be less than 1. If we do this, it becomes uncapped cone, same as the previous one. So it just goes into infinity, right, with those phases. Let's prove that this is true. So assume that V sub I lie on the level set, meaning that n dot product with V sub I is equal to H for any I. Okay? So we can consider a subset C sub D of this cone, C sub I, such that if X in C sub D, it means that the dot product Nx is less than or equal to D. Okay, so it is below level set D. Okay, so V sub I is in the level set H. C sub D is below level set D. Okay. Okay. Now let's remember that any point is being represented as this, right? So this expression here, we can replace X here with alpha I VI. That's what we do here. Okay. And this is equivalent to n, n transpose X, of course. But this n transpose X is less than or equal to D. So we have D here. But we also know that n times VI is equal to H. So we can transfer it to the left-hand side as H. Right? So what we have is sum of alpha I is less than or equal to D divided by H. Interesting. So for this sub-level subset C sub D, sum of I would be less than or equal to D divided by H. Okay, let's go on. Now we can define a new variable, beta I, which would be H divided by D alpha I. Right? And we can define new vertices double VI, which is D divided by H. So inverse of this, notice that they are opposite of each other, times VI. Right? So what we get is we obtain inequality. Oops, sorry. We obtain this inequality. Where do we get it from? Well, we get it from previous slide. It is this inequality, equality 19, but we replace alpha with beta, right? Alpha is replaced with beta. But remember that alpha is equal to D divided by H beta. So D divided by H beta. But now we can see something interesting going on. N times V is equal to H. So H divided by H is equal to 1, right? So we get rid of this part and we get rid of this part. Okay. But D here can be cancelled with this D here. So what we get is beta I less than or equal to 1. So this C sub D, so this subset of the cone under the level set D, is equivalent to, can be represented in VREP, in vertex representation, as all x such that x equal to beta I WVI, where sum of beta I is 0 and W and beta I is between 0 and 1. So you see we recovered original representation. But now we could choose any D and we get higher, right? So basically any sublevel set of this cone is V representation in the traditional sense. So geometry didn't change, everything is fine. But we can go high and high and high, we get bigger and bigger cones. So essentially when we got rid of this alpha less than or equal to 1, we just allow us to construct bigger level sets as big as we want. So we cut off the cap and we allowed it to go up. That's it. We did not break any other geometrical parts of the thing. Okay. Good. And I think this is this specifically is what people use in the literature, as far as I remember. So this is exactly the popular one. Now you understand where this comes from. All right.
One question, Professor.
Yes. Please.
If one of the alpha i's is equal to 1 or greater than 1, so all other alpha I should be zeros.
No. Because of this, right?
Yes, because of this.
Let me think about it. It's a good question, right? Is there something that I missed here? Yeah, I think you're right. That's a mistake. That's a mistake, my part. This should be also. We should get rid of this also. It should just be alpha bigger than 0. Yeah, I think that's the correct answer. Yeah, okay. I'll double check it after this lecture, but I think that's correct. That's correct. If what you said is true, if we leave this constraint intact, what will happen is since they cannot be negative, as soon as one of the alphas reaches 1, everyone else would be forced to be 0. And no alpha would be able to go beyond 1 because of this inequality. Yeah. So this constraint, I think, is correct. I think ultimately the level sets, there will be the same argument. It's just instead of 1, we would have something like D or whatever here for the level sets. But yeah, ultimately, I think this constraint should be strict enough for C sub A. For C sub D, we would have to retain it, but with a different value. Yeah, okay, a good observation. Very nice. It's very good. I will double check all of this after the lecture. Okay, now just final one example. Oh, yeah, final one example. So we could do all of this in this, I would say, almost high school manner, where I would say, okay, let's approximate friction cone by this expression. What is it? Well, this is essentially a square. I guess I can write like this. So it is just this approximation. Okay. Where we say in each of the parameter direction, in x direction and y direction, it should behave like a 2D cone. So instead of a cone, you get like just a pyramid. Right? Sounds very simple, but you can see it in the very good papers too. Like this expression 22, people use it in the very good papers. So 2D friction cone is not useless. Even as approximation, it is very nice. But yeah, in practice, people prefer this 4 faces or 6 faces, maybe 8 faces sometimes. Usually not odd numbers, and I've never seen anything more than 8 faces. So friction cones are quite simple. Like 6 faces is typical, I think. 4 and 6 faces. Right? Now, to get more information, you can read any number of papers, but specifically Stefano has a very good website, and like his papers in general are good. And yeah, as usual, the slides can be found here. Now that we covered friction cone, next what we are going to do is we're going to quickly discuss breaking contact. So what happens when the contact is broken, how it is described. And after that, we will be able to study modern techniques for quadrupeds, which would have to do with 2 things. One is simplified models. Another is MPC that is somehow simplifying the breaking and acquisition of contact, right? Those simplifications will be key, but we will discuss it in 2 weeks. So next week is breaking acquisition of contact. And after that, we will start on discussing modern techniques specifically developed for quadrupeds. Right. If there's no questions, then I will see you then.